This problem shows a prism-shaped object in a uniform electric field. I'm going to calculate the flux through each of the 5 surfaces of the object. Then I'll calculate the net flux. Electric flux is a dot product between the electric field vectors and an area vector of a surface through which the field is penetrating. So the first thing we should do is define what the area vector actually is. And so area vector is like a normal vector. Normal meaning perpendicular to a plane. So I'll deconstruct the shape a little. Going to pull that top surface out. And what we need is an area vector which is normal to the surface. Normal means it's perpendicular to it. So if we had lines on the surface itself, we need a vector which is perpendicular to any line on the surface. That could be something that looks like this. It makes a 90-degree angle with that line, a 90-degree angle there, a 90-degree angle will be formed here as well as here. And this is the area vector. We have another surface here. And if I draw lines on the surface itself, I need an area vector that is perpendicular to those lines. There will be another one of these on the opposite side. And the area vector for this one will point this way. This part can't be seen. We will have a bottom surface. That shape's area vector points down. And one more surface on the back side of it. And those are all the 5 surfaces. So the first one that I'm going to calculate the flux for will be the back surface. I think that's the easiest one. The reason is that the field lines, which we'll label as E, are anti-parallel to the area vector. Okay. Now, if you studied the dot product in Physics 1, you know that a dot product involves the magnitude of the first vector and the magnitude of the second vector, and then a cosine of an angle between them. We see here that the angle of the E vector is totally 180 degrees opposite of the A vector. So that's going to be a theta of 180. Let's give all the surfaces letters. We can call this surface A. This one can be B. This can be C. And then we have D and E. Let's find the flux through B first. The symbol for flux is the Greek letter capital omega. Has a subscript E for electric flux. And we want to just multiply the magnitude of the field times the area of the surface, which we can calculate here as 1 times 4 meters. So it's 4 meters squared. And we need a cosine of 180. This gives us a flux of -4 Newton meters squared per coulomb, and those are the units of flux. Now, what does the negative signify? It signifies that field is flowing through an area or into a volume. That's what the negative denotes. Now, it's going to be a little tougher to find the flux through A. The field lines will just continue going in the direction that they're going. And what makes this tough is we have to find out what the angle is between the field and the area vector. We can do it with a little bit of trig. It says here that this angle is 30 degrees. So the angle that A makes with E will actually be 60 degrees. Now we'll calculate the flux through A. Use the field strength. And we need the area of that shape. So it looks like it's going to be 4 times 2, 8 meters squared. And we'll have the cosine of 60 this time. That's 4 Newton meters squared per coulomb. And notice that it's positive this time. It's positive this time because field is flowing through a surface out of a shape. When it comes to the other surfaces, we're going to find that there's no flux through them. The reason is that the field is 90 degrees to the area vector. And when that happens, no field lines are actually penetrating the surface. It's like they're going right over it, but not through it. And so, for C, D, and E, the electric flux will be 0. Now that we have these values, we can find what's called the net flux. To calculate the net flux, we just want to add up all the individual surface fluxes that we had calculated. we see that the net flux is actually 0. We'll see later that this has implications when it comes to what's inside of the shape. Notice that the same number of field lines that come in also leave. You can count them up. We've got 1, 2, 3, 4, 5, 6 field lines penetrating the back surface, and 1, 2, 3, 4, 5, 6 field lines penetrating the front surface. According to Gauss's law, this information can tell us that there must be no net charge inside the volume. If there was a net negative charge, then more field lines should flow into the box than flow out. If there was a net positive charge inside the shape, then more field lines should flow out than flow in. Here we have a balance where the same number of field lines flow in as flow out. So that tells us there must be no net charge inside that volume.